In today's webinar, we are going to be discussing how to create a sign-on-random test using field data. And this is the culmination of a project that we've been working on for the past couple of months since the beginning of the year. And we are very excited to release this first iteration of this process. And there is future development that we plan on doing to improve this process and to uh, make it spread across more industries and more applications. But this is the first iteration, and as I said, we are very excited to get this out into the hands of the public and have this tool available for people to use. So as always, I start the webinars out with our core values: collaboration, capable and competent, accountable and responsible, strong and driven work ethic, do the right thing, and innovation. And this project really has been a collaborative project. We are very thankful to the customer that we did work with in developing this. This is a project that I personally have been working on for several years, it feels like, um, over troubleshooting certain issues and trying to figure out how to replicate in an engine environment on a shaker. And we'll talk a little bit about the problem that started this all out. I'm not going to go into any details at this point. We hopefully will have a case study that dives into the details getting sent out in the next couple of months. So this is, I mean, really a lot of collaboration and innovation, and then trying to improve the way that we analyze and develop tests for an end use environment. So over the past week, last week Thursday, this past Tuesday, and now today, I've been doing a series of webinars that talk about generating tests based on real world data. We talked about random import and fatigue damage for generating a random test. We talked about using shock response spectra and user-defined transient for generating a shock test. And now we're going to look at a bit more of a unique environment where I have some rotational component that generates dominant sinusoidal content in my real world environment that needs to be appropriately accounted for. And that dominant sinusoidal content needs to be run on a shaker using sine tones, but we still have this random background from whether it be driving down the road or whatever our normal random environment would be. So we need to combine those two in the end test that is generated. So as part of this, we have gone through and created a procedure and the appropriate analysis tools for analyzing the rotational component, extracting that from a time history file, building a sine tone profile or series of profiles that are appropriate and can be accelerated for the rotational sinusoidal environment. And then we use the fatigue damage spectrum for the remaining content, which would be our random environment after we've extracted that rotational tone or tones out of the real world waveform. So we'll step through this in presentation format a bit, and then we will actually jump in and just walk through a time history file and demonstrate this process and the test that gets generated in the end. So this all started a few years ago. When I travel to see my family, I stop and visit a series of different customers. And one of the questions that was posed to me on this customer visit is we are running a random test on our shaker. And this random test is built using the fatigue damage spectrum. And the time history data that we have is from an engine environment. The problem that we are running into is this engine environment has dominant sine tones, but when we analyze that environment with just FDS and convert everything into random and run the test, the failure that we are generating on the shaker using a random test is not the same failure that we're seeing on our engine mounted test, because this was an engine mounted component. So failure times were relatively similar, but the failure mechanism, the actual failure that was being generated, was completely different than the failure that was being generated on the real engine test. And that's a problem. So we looked at the data and we dived into analysis, and the customer really dove into the analysis and figured out that, okay, we have to replicate this environment in a better way, and that should be done through a Sine-on-Random test rather than a pure random test. So we did a bunch of research, a bunch of background, and there are other software tools that can be used to accomplish this task. But in understanding all of this and in diving through this, the software tools that the customer was using in order to generate the Sine-on-Random test were very intense. It required a lot of knowledge of that particular software. It required a lot of knowledge of vibration testing in general, and really ended up creating a long, drawn out process where a single test could take upwards of 30 hours of processing and tweaking and manipulating time in order to generate a single test. They'd run the test, figure out something wasn't quite right, and have to repeat that 30 hours worth of design and development in order to get a new test to make another attempt. So this time intense and the personnel requirements of somebody that actually understands these other software utilities were pretty high. And the goal of this entire project was to develop a tool that was easy to use, fast, and still generated appropriate results. So now let's take a look at the solution that we came up with, and it is going to be in ObserveView, our analysis software. It's used for analyzing time history files, real world environments, and it's called Sign Tracking Analysis and Generation, or STAG, S-T-A-G, STAG. So the first thing that we do is a basic order analysis and some order tracking. Now, we are looking at a rotational environment, something that is an engine environment. So our sinusoidal content is generated by the rotation of the engine, and we're looking at orders, which is essentially the number of events that are occurring per revolution. So if I have an engine running at 1,000 RPMs, and I have an event, some transient, some spike, some event that occurs once per revolution, that's going to be a first order event. If it occurs 3 times per revolution, it'd be third order, and so on. Order tracking is a mechanism in software that allows us to utilize the RPM trace as a reference, the RPM data as a reference, and shape tracking filters around the frequency of RPM and display that data appropriately and how data is changing based on the change of RPM. The initial release of this is designed to analyze engine ramp up or coast down type environments. And it can be used for engines, gearboxes, transmissions, any of these events or these environments that have these ramp up or coast down type evaluations that are done. So here is an example. Actually, this is the data that we will be looking at in the software. So I have the pink trace at the top is my RPM trace, and then I have acceleration data that is measured in association with that change in RPM. We can use a tach-based spectrogram, so a tachometer-based spectrogram, to plot that data on an RPM versus frequency graph. This allows us to see kind of that dominant sinusoidal content in those lines that you see that are more highlighted, that indicates the sinusoidal or rotational content. You can see that I have my cursor over the 6th order content in relation to that RPM trace. ObservView can automatically analyze this and indicate which orders are the top orders for that particular graph that's being displayed or this particular channel. We can also manipulate this and view the specific acceleration versus RPM data associated with that particular order. I can also look at the FFT slice that is associated with a particular RPM. So here I have on the bottom an acceleration versus frequency plot, and on the right-hand side, my acceleration versus RPM plot that are color mapped with the same colors that I have in my spectrogram for ease of viewing, reporting, and it just makes it relatively simple to understand and see. So once we get these orders analyzed and we've understood what orders we want to extract from that real world data, we can use the stag tool to actually accomplish that and accelerate the sine tone profiles that are generated. We use the inverse power law to accelerate our tests. And that requires material property, which is related to that B value in the formula on the right-hand side. M equals -1 over B, so they're directly related to each other, but that is the slope of the SN curve for the material that is being tested. We then define a target life, a test duration, and the number of sweeps. And this allows us to do the sine tone profile generation. I can manipulate those sine tone profiles to be dwells if I have very sharp resonances and I want to dwell at a particular frequency. If I want to do something very similar to a ramp up or a coast down, I might just generate a sine tone profile for each of those dominant harmonics, or the dominant orders and their harmonics, or my top 10 orders, and use that to generate a series of sine tone profiles that sweep across that frequency range exactly as they would in a ramp up or coast down. This is for presentation purposes. If you want to look at this presentation later, I put this in here. This is kind of what the stag software looks like and the indicators and the main boxes that you would use. So you select the appropriate channels, you set your test acceleration parameters, and then you can view, in this case, I have my top 10 orders, which can be automatically entered through the software, or you can manipulate this and add whichever orders of interest that you would like. Once we have all of that done and the sine profiles developed, we actually export to Vibration View to complete the test profile generation and the FDS analysis. So we have the sine tone profiles that we created in ObservView that are exported to a Sine-on-Random test. Those sine tone profiles are set appropriately with the right sweep rate and the number of sweeps, etc. Then we need to look at the remainder after we have extracted our selected orders from the real world data. So I have my original environment and I take the selected orders and extract that content out of the original data, leaving what would be just the random component for my random part of my Sine-on-Random test. So we analyze that using FDS, the fatigue damage spectrum that I talked about last week. And we can accelerate that random test using the same parameters as the Sine-on-Random test, and then merge the two, sine tones and random, to create that Sine-on-Random test profile. Some of the benefits that we will touch on, as I talked about in the beginning, it took upwards of 30 hours to develop a test using the other tools that our particular customer was using. In this process, we can do it in just a few minutes. We have automated profile development. The process is incredibly simplified, but still provides appropriate feedback and statistics to make those good engineering decisions. Modifications, any changes that we make are displayed immediately, and the profiles that are generated, the actual sine tone profiles, will have a large number of individual points. So you get a very good representation of the sine tone profile, and you don't have to, the software picks those points automatically rather than having to go through and manually find whatever points of interest need to be defined and generate a manual sine tone profile based on order analysis. So with that, let's just jump right into the demonstration and walk through this procedure and walk through it as it was designed to be implemented for this particular application. All right, so the first thing that I'm going to do, let's get rid of this, going to open ObserView 2020. And this is available for download on our website. It was released, I believe, yesterday. So if anyone is looking for the latest and greatest ObserView and you are eligible for, well, anybody can download it and do the basic analysis. Some of these additional features that we'll be looking at require paid licenses. But this is released to the public. So we're going to open a recording. And I have a recording here called Sample Order Data. This is directly from our customer. I just cleaned it all up so that there's no reference to whatever they may or may not be doing or their components. So here I have an RPM trace and then the associated accelerometers. We have accelerometers mounted on the engine itself and then out at the device under test. If we look, let's get rid of these three. Let's just look at this worst case here, or this nice. You can see that I have some pretty sharp peaks that are generated as I increase my RPM. I can go to the order analysis tab in ObserView and add a TAC spectrogram. So this is going to be using that RPM trace as a reference, and it is going to build a spectrogram for me based on RPM versus frequency. I can manipulate this in a lot of different ways. If I want to change my lines, sample, or window function, I might want to use something like a rectangular or a flat top just to get a little bit better amplitude. I can change my lines. Essentially, the spectrogram is just a series of FFTs using these settings overlaid on top of each other. So there I have my spectrogram. This is 600 frames. We're only going out to 500 Hertz. And if I keep going down here, I can see some additional cross-section graphs. So the one that I was looking at earlier is this order cross-section plot. And I can maneuver that. Let's just make this full screen so everybody can see it. And maneuver this a little bit so everyone can see. If I grab this order trace, I can highlight different orders, see the acceleration versus RPM slice for that particular order. So there's another one. I can also show either a horizontal cross-section, well, I can show horizontal and vertical or order. And so I could manipulate my vertical cross-section, put that one up here and say for, in this case, 2,158 RPMs, this would be the FFT for that particular RPM. And I can move that up and down as well to see how that peak changes. All of these graphs have cursors on them. So if I wanted to insert a point here, I can see that that is 1.79 G's peak. If I move, let's look at our actual, there we go. Here we have, that was the order or the time data that I was looking at was this DUT lat. So there I can see that as well. So I could proceed with this analysis just looking at this. If we change our parameters here, if we make our max something a little lower, this has, let's just do 10 G's. It's just going to bring some of those peaks and bring some of that into better view. I could even change my minimum if I change my min to half. So I'm just changing the scale of my color spectrum here to emphasize some of these points and these orders more appropriately. So that is essentially the order analysis. In the STAG process, this is mostly just for understanding what is happening. I don't even have to look at this. The software will do most of this for me. The next thing that I'm going to do is click this Add Top 10 Orders button in the top left-hand corner. And what that does, if you can see that, there are all red dashed lines over top of the top 10 orders for this particular channel. I could look at those if I wanted to. See what I would see. Now, all of this data, if I wanted to look at this in some way, so if I just plot that, I can right click on this, hit copy graph, and I could paste that right into Word or whatever other text-based plot I was looking at. I can paste that right in. It gives me my spectrum. Then if I wanted to see this, I might rotate this graph on the bottom here so that it's now acceleration versus RPM. Makes a little bit more sense that way. I could hit copy there and paste, and I can see all of that data get plotted on a graph. All right, so now let's look at the STAG portion of this process where we actually start to take some of these orders and analyze them so we can convert them into sine tone profiles and actually accelerate this test. All right, so we're going to use the STAG button in the top left-hand corner of the order analysis ribbon. Now what this is doing is slightly different. The plot that I'm going to have displayed on this is going to be different than the spectrogram data that I have displayed on my spectrogram. The spectrogram data is going to be FFT based. In this case, this is actually tracking filters shaped around the RPM reference trace to extract and determine what the sine tone peak amplitudes are for each of the orders that I have displayed. So the spectrogram data is FFT based. This is tracking filter based. So this is going to be very accurate. Now for each of these different orders, I can see the starting frequency and the ending frequency. I can look at the Q of the primary resonance. I have some that have very sharp peaks in them. And if I were running this on a shaker, I may want to manipulate how I run this test. For those very sharp resonances, I may want to do a sine dwell. And if I wanted to do that, I could edit this tone and change the segments So I could just simply do a narrow band and I could set a center frequency and have a tone that oscillates just at this very highest frequency point if I wanted to. I can also see, if I keep looking at my tables here for all of the statistics of this order, it has a peak amplitude of 29 Gs at 172 Hertz, peak velocity of 10.4 inches per second, a peak displacement of 0.10193 inches, an average amplitude of 4.78 Gs. So I can look at all of these, and if I highlight all of them, so if I click on one, I have my 3 channels, and then the enveloped and accelerated trace. If I look at just the, or if I look at all of the orders, I can again see all of those enveloped and accelerated traces and all of the lower level, the original order traces. My test acceleration parameters and my material property, target life, test duration, and total number of sweeps, RPM range. I also have to set, or can set, my FDS parameters for the random analysis that I'm going to do in vibration view. We just export that all as one. So again, I could go through and manipulate all of these and pick peaks and fine tones, but we're just going to run all of them and let them all sweep with the same sweep rates that they sweep up and down together. Can manipulate filter settings for the TAC filter width. If I make this tighter, it's going to reprocess my data and use a sharper tracking filter or a sharper TAC filter so I might get more or less ragged. I can also change my tracking filter width for my peak amplitude measurements. So now we're going to take 1, 2, 3, 4, this is 10 tones. Let's take all of those. Let's take all of those and export them to vibration view. So this export to vibration view is accomplishing, let's do webinar demo. This export is accomplishing a few different tasks. First, it is exporting the accelerated sine tone profiles. Second, it is extracting those selected orders, that selected order content, out of the original time history waveform, and then generating a new time history waveform that is the original time history data minus these selected orders. And when I do this, vibration view, the test settings window is automatically going to open, and the FDS processing is going to start on this order data, which is the original time history data with the orders or the selected orders extracted from it. Let me look at a few questions here. All right, we'll look at that here in a minute. I'll answer those questions afterwards. I was looking for simple ones. Those are a little bit more involved than what I can answer right now without clicking around the software. So this is going to go through and process, and we are going to use those FDS acceleration parameters. And once it is done, we will have the opportunity to look at our test settings. If we wanted to, we could add kurtosis or kurtosis to the random portion. So there I have the FDSs of what is remaining from with my orders extracted. I'm enveloping all of those together. On my Sine-on-Random tab, I have all of my sine tone profiles entered. Now, what you will notice once we actually save this and start to run it is that some of my sine tones are too low in amplitude, meaning that they're either below the random or inside of the random band. And the way that we control sine tones in Sine-on-Random is using a tracking filter. So that tracking filter is inclusive of the random content, and it's going to cause some variation. So in order to get this test to run, what I would need to do is I could, for each tone, create custom limits that allow me to change the abort limits for that particular profile. And I could go through and do that for all of these, but for the sake of the demonstration, I'm just going to change the Sine-on-Random parameters. We're just going to open up our abort limits so that we don't have to fight that while we run the test. So I have my sine tones with my appropriate sweep rate. I have on my Sine-on-Random parameters, I have all of these various parameters. I could increase my tracking filter if I wanted to. That's dependent on sweep rate, but these are the same parameters that we see in a typical sine test. I can also do notching on the sine tone specifically. So if I know that I'm never going to exceed a particular limit, I could do that. All right. So let's just look at these. Those all look good. Hit save as, and we'll save that. It's going to give me the option to open the file. So I'm just going to jump right in and we will open this. I'm going to close ObserView for the time being. Let my controller connect here a minute. And I went through and built a custom graph layout for this. I have a 10-tone Sine-on-Random graph layout that I'm just going to open here so that we can all see exactly what is going on. Make that a little bigger. There we go. And we'll stick this one here. So now I have my 10 Sine-on-Random tones that are all completely different. You can see that they're all appropriate. And if I hit start, this is going to come up to level and we're going to see those start running. Now, again, what you will notice is that some of these tones, especially when they have these lower amplitudes, they are going to show the randomness of random. So they're going to be more ragged. But as they increase into the higher amplitudes, you're going to see them get much tighter in the tracking filter, differentiate more clearly between the random and the sine tones that are being run. So as this comes up, we'll transition over to running and we will start sweeping our tones. So it's just bringing the random up to level. And sorry about that. Click the wrong button. Might have to use a slightly tighter tracking filter to smooth this out a little bit. I could also, what it's waiting for is my tolerances. So if I make this a little bigger, it will fix the problem. So I could have manipulated this. What you can see is some of these tones, like this one in particular, is inside of the random. It creates a little chaos in the sine tone profile calculation. You'll see that in these sine tone profile graphs that are displayed, that they have a lot of raggedness at this extreme low frequency because those sine tones are essentially inside of the random. As that disparity gets bigger, as those sine tones get further and further outside of the random band or outside of the random component where it's not, where the random isn't contributing as much, then you'll see that smooth out and be lower, where the variance of the sine tone profile will be much less. So that is really the brief kind of overview of how this works. So let's have a look at some questions. All right, where can you find more information on the different window functions and why you might want to use one versus the other? Yeah, so in ObserView, we tried to do at least a bit of a conversation or give you some hints as to what you can do for window functions. So if I open this particular one, this recording, in the top here, we have all of the same window functions. And in the description down here in usage, you can see that it's similar to Blackman and Hamming, what the main lobe width is, and how it is superior or worse than some of the similar ones. If I look at rectangular, it shows usages for periodic signals or signals shorter than the length of the window. Flat top is going to give you accurate amplitude measurements. It'd be good for calibration, but when you use the flat top, you sacrifice the accuracy of the frequency resolution. You can also go to our help file. If I click help and make this stand out for everyone, it will take me to, I make this a little bigger, get this out of the way so I can see, the table of window functions and give you a description of all of them, what their characteristics are, what they might be used for, and what they look like. It also gives you an effect or conversation topics about what the main lobe width, side lobe height, roll-off rate, and bandwidth, what the effect of manipulating those would be. So the help file and ObserView are a great tool for that. If I had a histogram of percent time at engine RPM, can I weight the sine tones to account for this? That's literally a conversation that I had with our development team this morning. That would be something that we would be very interested in developing, but it is not implemented in this version of the software. If you can reach out to me, my email is jade, J-A-D-E, @vibrationresearch.com. I will send you. So this would be something that we would be interested in developing, but we need a partner in order to do that, or somebody that has the real world data and the knowledge and the forethought of really understanding what the end goal is. And we would be very willing to look into that. So since you have multiple sinusoids, does this reduce test time compared to a single sweep? Yes, just like sine-on-sine testing, which is becoming more and more common in Europe, where rather than running a single tone from 20 to 2000 hertz for 5 minutes, or let's just pick a good number, I could do 12 minutes, I can divide that tone into 4 parts and run 4 tones over that frequency range. It's very dependent on what you're doing. and the application. But in effect, yes, you can reduce the test time of a single sweep by dividing it into four tones running over the same frequency range. The next question, sine tones are removed from the data prior to running the FDS, so you aren't over accelerating, having effects of high sine tones driving into your FDS analysis. Absolutely correct. We are extracting the selected order content out of the original waveform so that when we do the FDS analysis, we're only doing that on the random component and not being affected by the sine component that has already been extracted and isolated. Can you display the vibration time history waveform with the orders removed? Sure, if I can find it. So the software, if I go to Observe View, let's go back to this. If I do File, Open, I'm not exactly sure where we're saving it. It should be in here. So there's Webinar Demo, Export. So this is going to be the file that I created. So there is the remaining random background. And if we, let's just put these two side by side. Oop. I'll just open another instance so that we can see them side by side. And we'll stop this test to try to keep my computer from exploding. Move that one over here. So if I look at my original versus this one, close that, close that. Let's hide these three. So we're just looking at hide that one too. All right. So there are the two waveforms. And if we just look at something like, oh, a PSD, you should be able to see the difference pretty clearly. Add PSD. So my overall levels are quite a bit lower. You do have some sine peaks in there just because that's how the data is. But, oh, and I'm only looking at a few seconds. Let's do unlock. There we go. Sorry about that. I had the wrong settings. I have it locked to 12 degrees of freedom. So there we can see the overall levels. If I look here, I'm kind of at, this is right before 100 hertz. And let's do 94 hertz. So there you can see I went from 0.0, so that's lateral, 0.06 down to 0.02 G squared per hertz at that frequency. So it is decreased significantly with those tones removed. And I could go through and merge everything and put them in Excel and do a little bit more of a analysis, but that's outside of what we're trying to talk about today. All right. Is this process just as effective with field data collected from an over-the-road engine running normal operation driving? So the question is this process just as effective with field data collected from an over-the-road engine running normal operation driving conditions, or is it best to use an RPM sweep to collect the data to be analyzed? The iteration, this software will only work with just an RPM sweep, either up or down. There may be benefits to using over-the-road data as we continue to develop more variants and more capability into the software. But the issue that you run into is all the noise and all of the variation. You don't get a very clean RPM trace. You don't get very clean data off of over-the-road tests. So it's very difficult to figure out and isolate the sinusoidal content and really clearly define where those resonances are without smearing effects. So this using an RPM sweep is going to be much cleaner, and it's going to result in a better application or a better test in the end is the word I'm looking for. All right. How do you decide whether to run Sine-on-Random or sine sweep testing? Look at the amplitude of your remaining random content and determine if it is high enough in amplitude and frequency range of use. It's just dependent on, that's an engineering decision. There's too many variables to give you this is what you should do and this is what you should not do. Deciding between a sine on random test, if I want to do a sine dwell or a sine sweep, could be, some of the things that you look for there is the Q of the resonance that's being excited. All right. Next. While working on tractor exhaust system, we have observed that accelerated time is lesser in sine sweep profile as compared to sine on random. Accelerated time. So I'm not exactly sure what this question is trying to say, but when you run just a sine sweep, a single sine tone at an amplitude, you are driving all of your energy into that specific point and are probably going to get the most energy driven into a resonance as you sweep through it. So you could get failures faster through a sine sweep, or especially if you're doing a sine dwell or sine resonance track dwell, you're definitely going to get failures faster. The problem is how do you relate that to the real world? And that's where the engineering decision has to be made. Hopefully this is a tool that we can provide. All right. Yikes, I'm trying to. So if you had RPM data on field load data, could you use stag to pull out rotational? So if I had RPM on field load, could you use stag to pull out the rotational influences from the field data based on order analysis from an engine dyno sweep? So if I had RPM data on field load data, could you use stag to pull out the rotational influences from the field data based on order analysis from an engine dyno sweep? Interesting. Current iteration, no. Future iteration, possibly. I think you'd have it. I don't know. I think you'd have a difficult time doing it. But there may be other ways. If your field RPM data, there may be a way that if we go down the road of having an RPM density profile that we end up creating, that you could analyze each RPM bin with certain parameters. Again, that's a fantastic question. In this current iteration, there's not a lot that I can do, but it would be something that same person. I add that to the list of questions to contact me about. how can we decide up to what frequency to be worked upon and up to what order should be worked upon while creating an accelerated profile? The easiest way to start is looking at the amplitudes that are being generated by your Sine-on-Random profile. As soon as your sine tone amplitudes start falling below the overall broadband random, they're really no longer doing anything. So at that point, adding more orders isn't going to benefit you anything. So you want, and it's very product dependent, very much an engineering decision. The beauty of the Stag software is that it is very easy to make changes, to add and remove things, to quickly see what those changes are. How are top 10 orders chosen? By the unit that it is being displayed in. So in this case, I have acceleration, so it's going to look at the peak accelerations, and there's a whole algorithm involved with that, but it's going to be based on peak acceleration. If I had a velocity waveform, it would be based on peak velocity. All right, that's my last question. Any more questions while we're still talking? All right. Oh, what should be the checkpoints to validate our accelerated profile with the actual results? So yeah, checkpoints. One is if you have a real world failure and it's being replicated, that's a good checkpoint. Two, you can repeat the same analysis or take a generalized FDS of your original environment that's just a one mass FDS and combine that with, or compare that to the FDS of the accelerated test and use that. Another direction that I'm looking to go in future development is to actually start doing cycle counting and have a way to display and view that so I can look at my real world data, accelerate it, calculate the appropriate cycle counts, and then compare that to the cycle counts from the shaker test. That would be a method. Yeah. So again, it's an engineering decision, but you have to be careful not to over accelerate the profile. You have to be careful. You know, I can't run a 10,000 hours worth of life in 10 minutes. That's not really how it works. So you don't want to over stress the item, but you do want to accelerate the test. Comparing your test results, the actual failures generated, or the test results in themselves to the original data with the same acceleration parameters would be the best method. What should be the exaggeration factor while creating an accelerated profile? Depends on the product. So there's ways to evaluate it, looking at the SRS of the long time history and making sure you don't exceed 10x of the SRS or 5x of the SRS. It's very dependent on the product and on what you are testing and how it's tested and how much your resonances are being amplified and how sharp your resonances are, etc. There's, again, that's one of those questions that there's a lot of different evaluations and different possibilities. All right. Well, I want to thank everyone for their time today. I appreciate taking the time out of your day to come and sit and listen to me talk and help and watch this demonstration. As I said, we've got a few months of work into this project, and we are very excited about what we have implemented so far and look forward to continuing to work with other customers to make this even more improved and continue to implement more features that make this more applicable to a wider range of industries and applications. Had some great suggestions today. Look forward to feedback from those and to working with all of you as we go down this road. If you have any questions for me, please feel free to email vrsales@vibrationresearch.com, and we will do our best to answer the questions, or start working on feature requests and implementation into the next version of the software, into the future versions of the software. This is how we develop software. A lot of our innovations and a lot of the changes that we come up with are all based on customer request, and it really does benefit a lot to have somebody with a real application that they need a solution for. And given that chance, we have a lot of software developers and a lot of knowledge here that can take your dreams or what you spend a lot of time doing and turn it into something that can be run in our software and can be done faster, simpler, and accurately. Thank you again for your time and have a good day.